This lecture is going to cover two-factor analysis of variance, or two-factor ANOVA. Suppose we want to measure the physical endurance score on a scale from 1 to 100 for a random sample of males and a random sample of females, each of whom is given one of two different dosages of a dietary supplement, either a high dosage or a low dosage. Now notice here we have a quantitative response, physical endurance score, and we have two categorical predictors or factors, gender and dosage. The interaction plot down on the bottom right shows the sample mean for each of the four different groups. Now in two-factor ANOVA, we have three different questions that may be of interest. The first question might be, is there a difference in the mean physical endurance scores across gender? Looking at the interaction plot down on the bottom right, it certainly looks as if males have a higher average physical endurance score compared to the females. We could also ask, is there a difference in the mean physical endurance scores across dosage? And again, it appears as if high dosages are associated with higher physical endurance scores compared to the lower dosages. And finally, we could ask, is there an interaction between gender and supplement dosage? Looking at the interaction plot, it appears as if these lines are pretty close to being parallel, so it doesn't seem as if there's an interaction. But two-factor ANOVA gives us the method by which we can actually formally answer all three of these questions. Two-factor analysis of variance is a statistical technique that we use to compare the means of several groups whose categories are divided up across two categorical variables. Now, two-factor ANOVA uses four different sources of variability to compare the means across both of the individual factors, as well as to assess if there's some kind of an interaction between the factors. Notice that this is different from one-factor ANOVA, because if you recall from one-factor ANOVA, we only had two sources of variability. We had the sums of squares due to the treatment, and the sum of squares due to the error. In a two-factor ANOVA, both of your independent variables must be treated as categorical. And just like one-factor ANOVA, we can also represent two-factor ANOVA as a regression model. Now here's the notation that we're going to use for two-factor ANOVA. Factor A is going to be the row variable that contains our different categories. Factor B is going to be our column variable that has C different categories. And we'll let N denote the total number of observations per cell. In a balanced two-factor ANOVA, we require there to be the same number of observations in every combination of the factor levels or in each of the cells. So, unlike all of our previous situations, N is not going to denote the total number of observations altogether in the data. N is going to represent the total number of observations per cell. Let's talk about how to set up the two-factor ANOVA regression model. First of all, notice that the model must be defined using effect coding. Now, to model the response, we first have mu, which is going to be estimated by the grand mean across all observations. Then what we do is create r-1 dummy variables for the first factor, x, each with its own regression coefficient alpha sub I. Each dummy variable is then coded such that the value is equal to 1 if the observation is in group I, -1 if the observation is in the reference group, and 0 otherwise. For the second factor, z, we create c-1 dummy variables, again, each with its own regression coefficient beta sub I. The coding scheme is the same as with the first factor. Set the dummy variable equal to 1 if the observation is in group J, -1 if it's in the reference group, and 0 otherwise. Then we add on the interaction terms, where we interact every dummy variable for the first factor, x, with every dummy variable for the second factor, z. Each interaction term's regression coefficient is denoted by gamma, and finally we add on the error term at the end. So let's set up our two-factor ANOVA model for the physical endurance score data. We'll start out with y equal to mu, where mu is going to be estimated by the grand mean of all of our observations. Then we'll add on alpha 1 times x1. x1 is our dummy variable denoting the person's gender. We'll set x1 equal to 1 if the subject is male, and negative 1 if the subject is female. Then we'll add on beta 1 times z1, where z1 is the dummy variable for dosage. We'll let z1 equal 1 if the subject was assigned the high dosage, and negative 1 if the subject was assigned the low dosage. Now notice that because both of our factors only had two categories, we only need one dummy variable for each. As a result, we're only going to need one interaction term. We'll add on gamma 1, 1 times x1 times z1. The gamma 1, 1 is representing the regression coefficient that's interacting the first dummy variable from the first factor with the first dummy variable from the second factor. If we had additional dummy variables for one or both of our factors, then we would increment those subscripts in the gamma to represent which dummy variables are being interacted. Then to finish things off, we add on the plus e at the end. Let's take a look at the data now. Notice that we have a balanced two-way ANOVA. We have 4 subjects in each of the 4 combinations for a total of 16 observations. The table of group means down at the bottom is going to be extremely important for calculating out our sums of squares. In total, we have 9 different means that we're going to need to incorporate. 4 of these are the cell means, or the combination means. Males given a high dosage averaged 87 for their physical endurance score. Males given a low dosage averaged 51. Females given a high dosage had an average physical endurance score of 61, while females with a low dosage averaged 33. Then we have the row means and the column means, which average all observations in that row or column while ignoring the other factor. The 8 males had an average physical endurance score of 69, while the 8 females averaged only 47. Similarly, the 8 subjects given the high dosage averaged 74, while the subjects on the low dosage averaged 42. Finally, the last mean we need to be concerned about is the grand mean. Overall, these 16 subjects had an average physical endurance score of 58, regardless of gender and dosage. Let's talk about how to estimate these regression coefficients. Over on the left, we have y hat, which is the predicted value of the response. On the right, we start out with mu hat, where mu hat is going to be estimated by the grand mean, y double bar. Each alpha sub I hat is calculated by taking the mean of the observations in category I and subtracting off the grand mean, y double bar. Similarly, each beta sub j hat is calculated by taking the mean of the observations in category j and subtracting off again the grand mean. Finally, each gamma sub ij hat is calculated by taking the mean of the observations in cell ij, subtracting off the mean of the observations in category I, further subtracting the mean of the observations in category j, and then adding on the grand mean. Now, using our table of means, we can calculate out each of the 4 parameter estimates. Mu hat is going to be estimated by the grand mean, y double bar, which is 58, the average physical endurance score across all 16 subjects. Alpha 1 hat, which corresponds to the dummy variable for gender, is found by taking the sample mean for the males and subtracting off the grand mean. Now, we're using the sample mean for the males here because they were coded as 1 in the dummy variable. This is going to give us 69 minus 58, so alpha 1 hat is equal to 11. Beta 1 hat, which corresponds to the dummy variable for dosage, is found by taking the sample mean for the people given the high dosage and again subtracting off the grand mean. Like we did with gender, we're using the mean for the high dosage because this is the category that was coded as 1 in the dummy variable. This gives us beta 1 hat equal to 74 minus 58, which is 16. Finally, gamma 1, 1 hat is going to take the mean of the observations in the cell where both variables were coded as 1. This is the males who were given the high dosage. Subtract off the sample mean for the males, further subtract off the mean for the people given the high dosage, and then add on the grand mean. So gamma 1 hat will be equal to 87 minus 69 minus 74 plus 58, which is equal to 2. So in the end, our regression equation is y hat equal to 58 plus 11 times x1 plus 16 times z1 plus 2 times the interaction between x1 and z1. As I mentioned earlier, there are 4 different sources of variability in two-factor ANOVA. 2 of these are the between-group variation for each of the individual factors. The between-group variation for factor A, denoted SSA, measures how different the means for groups in factor A are from the grand mean, and the between-group variation for factor B, SSB, measures how different the sample means for the groups in factor B are from the grand mean. We also have between-group variation for the interaction term, which is going to be denoted SSAB. This measures how different the combination means or the cell means are from the grand mean. And finally, just like what we had in one-factor ANOVA, we have within-group variation, or the SSE. This is measuring how different the individual observations are within each combination of treatment groups, or how different each observation is from its cell mean. Now, calculating the sums of squares looks considerably worse than it actually is. The between-group variation for factor A is found by taking the group mean for each category in factor A, subtracting off the grand mean, squaring the difference, adding up the squared differences, and then multiplying by the number of categories in the column variable C, as well as the number of observations per cell, N. The between-group variation for factor B is found in a similar way. Take the sample mean for each group, subtract off the grand mean, square the difference, and add the squared differences together. Then we again multiply by the number of categories in the row variable, as well as the number of observations per cell. The between-group variation for the interaction term looks more complicated, but it really is just the same process. This is saying, for each cell inside the table, take the cell mean, subtract the row mean, subtract the column mean, add the grand mean, and then square the difference. The sum of these squared differences times n then gives us the interaction sums of squares. And finally, the within-group variation, the SSE, is found through this sum. Again, while it looks complex with the triple summation, all that we're really doing is taking each observation, y sub ijk, subtracting off the cell mean, squaring the difference, and adding all of these squared differences up. Let's start out by calculating the between-group variability for gender. This is going to be our SSA. What we'll do is we'll take the average physical endurance score for the males, 69, subtract off the grand mean of 58, and square the difference. Then we'll repeat that for the females. We have an average physical endurance score of 47 for the females, minus the grand mean of 58, that difference squared. We'll sum up those two squared differences, and then we'll multiply by the number of columns in our other factor, which is 2, times the number of observations in each cell, which was 4. This is going to give us 8 times 121 plus 121, giving us an SSA of 1,936. We can do a similar thing to calculate the between-group variability for dosage. This sum of squares is going to be denoted SSB. We'll start out by taking the average physical endurance score for the 8 subjects given the high dosage, 74. We'll subtract off the grand mean of 58 and square the difference. Then we'll add on the difference between the average physical endurance score for the subjects given the low dosage of 42 minus the grand mean of 58 squared. We'll take that sum and multiply it by the number of categories in the row variable, which is 2, times the number of observations per cell, which is 4. This gives us 8 times the quantity 256 plus 256, giving us an SSB of 4096. Now, because we have 4 cells in this table, 4 different combinations of our two factors, we're going to have 4 terms that make up our interaction sum of squares, the SSAB. The first term is going to come from the males who were given the high dosage. We'll take their cell mean of 87, subtract off the row mean of 69, further subtract off the column mean of 74, and add on the grand mean of 58, and square that entire calculation. Their contribution to the SSAB is going to be 4. We do the same thing for the males given the low dosage. The cell mean of 51, minus the row mean of 69, minus the column mean of 42, plus the grand mean of 58, squared, again gives us 4. For the females who were given the high dosage, we take the cell mean of 61, subtract off the average physical endurance score for the females, which was 47, further subtract off the column mean of 74, and then add on the grand mean of 58, squaring that whole thing, again gives us 4. And finally, for the females who were given the low dosage, we take their cell mean of 33, subtract off the mean for the females of 47, subtract off the mean for the subjects given the low dosage of 42, add on the grand mean of 58, square the whole thing, and we again get 4. The SSAB is then calculated by taking the number of observations per cell, which is 4, and multiplying that by the sum of each of the individual contributions that you see from our 4 different groups. 4 plus 4 plus 4 plus 4 gives us 16, so our interaction sum of squares, 4 times 16, is 64. The final sum of squares that we need to calculate is the within-group variation, or the error sum of squares. Now recall that this looked quite complicated, but all we really need to do is find the squared deviation between each observation and its corresponding cell mean. Now the first 4 observations in this table are giving the contributions for the males who had the high dosage. Their actual observations were 91, 83, 86, and 88, which you see in the third column. This comes out to an average of 87, which is contained in the fourth column. The difference between each observation and its corresponding cell mean is then contained in the fifth column. For the males who were given the high dosage, they were 4 points above, 4 points below, 1 point above, and 1 point below the cell mean. Finally, the squared difference for each observation is contained in the final column. We then repeat this process for every remaining group: males with the low dosage, females with the high dosage, and females with the low dosage. The error sum of squares, or the SSE, is going to be the sum of all of the values in the final column, which is equal to 314. Now let's talk about the different hypotheses that we can test in TwoFactor ANOVA. There are actually 3 sets of hypotheses that we can test. The first one that you should always test deals with the interaction. We have the null hypothesis that no interaction exists between factor A and factor B, against the alternative that an interaction does exist between factor A and factor B. The last 2 sets of hypotheses deal with the individual factors. We can then test the null hypothesis that the means for the treatments in factor A are all equal, against the alternative that the means for the treatments in factor A are not all equal. Similarly, we have the null hypothesis that the means for the treatments in factor B are all equal, against the alternative that the means for the treatments in factor B are not all equal. In terms of assumptions and conditions, we need to make sure we have independent random samples from each of the populations. We need to make sure that the dependent variable is normally distributed within each group. And we need the variance of the dependent variable to be about the same in each group. For each set of hypotheses, we have a different test statistic. Notice that there are 2 similarities across all 3 of these test stats. Each of them follows an F distribution, and the denominator is the same in each of the test stats. Each of them has a denominator equal to the sum of squares due to the error, SSE, divided by the number of categories in the row variable R, times the number of categories in the column variable C, times n minus 1, where n is the number of observations per cell. The numerator, however, is different in each of the test stats. To test for a significant interaction term, we take the interaction sum of squares, SSAB, and divide by its degrees of freedom, the number of categories in the row variable minus 1 times the number of categories in the column variable minus 1. To test if the means for the treatments for factor A are significantly different, we have the sum of squares for factor A, SSA, divided by the number of categories in the row variable minus 1. And to test for differences in the means for factor B, we take the sum of squares for factor B, SSB, and divide by the number of categories in the column variable minus 1. So let's work through each of our three hypothesis tests. First, we'll test for a significant interaction term. The null hypothesis is that gender and dosage do not interact, and the alternative hypothesis is that gender and dosage do interact. The test statistic is going to follow an F distribution. In the numerator, we have the interaction sum of squares, which is 64, divided by its degrees of freedom. We have two categories in the row variable and two categories in the column variable, so we have 2 minus 1 times 2 minus 1. In the denominator, we have the SSE of 314 divided by the number of categories in the row variable, which is 2, times the number of categories in the column variable, which is also 2, times the number of observations per cell minus 1, which gives us 4 minus 1. This means we're going to have 1 degree of freedom in the numerator and 12 degrees of freedom in the denominator. So our test statistic is going to be 64 divided by 26.17, which gives us 2.45. Now the critical value with 1 and 12 degrees of freedom is 4.75, and the corresponding p-value here is 0.1438. What this means is that we fail to reject the null hypothesis and conclude that gender and dosage do not interact. Now we can test to see if the mean physical endurance scores are the same across gender. We have the null hypothesis that males and females have the same mean physical endurance scores, against the alternative that males and females do not have the same mean physical endurance scores. The test statistic is going to be the sum of squares due to factor A, 1,936, divided by the number of categories in the row variable minus 1. The denominator here is going to be the exact same denominator as what we had for the test for interaction, 314 divided by the quantity 2 times 2 times 3. We're again going to end up with 1 and 12 degrees of freedom, and our test statistic is going to be 1,936 divided by 26.17, which gives us a test stat of 73.98. Because we have the same degrees of freedom, we'll have the same critical value, which is 4.75, and our test stat corresponds to a p-value of 2 times 10 to the negative 6 power. What this means is that we can reject the null and conclude that males and females do have significantly different mean physical endurance scores. Finally, we can test to see if the mean physical endurance scores are the same across dosage. Here, we'll have the null hypothesis that high and low dosages yield the same mean endurance levels, against the alternative that the average physical endurance levels are not the same across high and low dosages. The test stat again is going to be the sum of squares due to this factor, which was 4,096, divided by its degrees of freedom, 2 minus 1. We then divide that numerator by the exact same denominator, 314 divided by 12. Again, we'll have 1 and 12 degrees of freedom, working out the calculation of 4,096 divided by 26.17 is going to give us a test stat of 156.54. Again, because we have 1 and 12 degrees of freedom, the critical value is still going to be 4.75, and this test corresponds to a p-value of 3.03 times 10 to the negative 8. What this means is that we can reject the null and conclude that the mean physical endurance scores do differ between high and low dosages. Now let's talk a little bit about comparing the means, because we have a couple decisions that we need to make. After performing the two-factor ANOVA, the comparisons that we can ultimately make depend upon the results of the tests. Now, we can use either Tukey or Bonferroni confidence intervals, but because Bonferroni requires us to change the level of confidence, Tukey is generally easier to use. But all of these calculations are complex, so it's best to use Minitab anyway. Now, the decision that we make depends on the result of the interaction test. If we find that we have a significant interaction term, then we can only compare the combination means with one another. The reason for this is because factor A changes depending on the level of factor B. So we can't analyze the means independently of one another because these factors are related. However, if the interaction term is not significant, then the levels of each factor can be compared independently of one another. In our physical endurance score example, we found that the interaction term was not significant. As a result, that allows us to compare the main effects independently of one another. We can look at the average physical endurance score of the males and directly compare that to the average physical endurance score for the females. We can do the same thing for dosage. We can directly compare the high dosage against the low dosage without being concerned that there's any kind of an interaction between gender and dosage. Now, the way that we can make these comparisons is by calculating out a confidence interval for the difference between the means of each pair of factor levels. Using Minitab, we can obtain 95% Tukey confidence intervals for the difference in each pair of group means for gender and dosage. Comparing the males and the females, if we take the average physical endurance score for the males and subtract off the average for the females, the difference in the sample means was 22, and that gave us a 95% confidence interval of 16.43 to 27.57. If we do the same thing for high dosage minus low dosage, the difference between the means was 32, and that gave us a confidence interval of 26.43 to 37.57. Now, these confidence intervals reveal a couple of things. First of all, we can conclude that males have a significantly higher mean physical endurance score compared to the females. And second, the subjects who received a high dosage had a significantly higher average physical endurance score compared to the subjects who received the low dosage. Let's take a look at an example where there is a significant interaction term. Suppose we want to compare the heights in inches of 30 plants that were given either low, high, or no sunlight, and each was watered either daily or weekly. Our first set of hypotheses is going to deal with the interaction term. The null hypothesis states that there is no interaction between amount of sunlight and watering frequency. The alternative states that there is an interaction between amount of sunlight and watering frequency. The second set of hypotheses deals with watering frequency. The null hypothesis says that the average height of these plants for being watered daily and being watered weekly are equal, against the alternative that the average heights for being watered daily and weekly are not equal. And then finally, we have a set of hypotheses for amount of sunlight. The null hypothesis states that the average heights for low, high, and no sunlight are all equal, against the alternative that the three means are not equal across the different sunlight levels. When you run a two-factor ANOVA in Minitab, this is the type of output that you'll get. Notice that we have a different row for each set of hypotheses. We also have a row for the error term and a row for the total. In the second column, we have the degrees of freedom. Notice that because we have two categories for watering frequency, we're only going to have a single degree of freedom. But because we have three categories for sunlight, we're going to have 2 degrees of freedom. This extra category for sunlight is also going to cause us to have an extra degree of freedom in the interaction term. So let's start to work through each of these tests. For the interaction test, we have a test statistic of 7.43, which corresponds to a p-value of 0.0031. We'll reject the null hypothesis and conclude that a significant interaction between watering frequency and amount of sunlight does exist. For watering frequency, we have a test stat of 50.5, which gives us a p-value that's less than 0.0001. We'll again reject the null hypothesis and conclude that the average heights of these plants do differ across different watering frequencies. And finally, for amount of sunlight, our test statistic is 126.07, giving us a p-value less than 0.0001. We'll again reject the null hypothesis and conclude that the mean heights of these plants differ across different sunlight levels. Now we have to figure out how we can compare the group means. Because we have a significant interaction term, we're only able to compare the combinations of the treatment levels. The reason for this is we can't interpret the main effect if the interaction term is significant, because the average height for the plants at one level of watering frequency changes depending upon the sunlight level and vice versa. So in order to compare the different combinations of the treatment levels, what we have to do is obtain grouping information about each of our 6 different combinations using Minitab. When you obtain the grouping information from Minitab, you'll get an output similar to what you see over on the right. Now the first column is giving you every single combination of your factors. In this case, each watering frequency interacted with each amount of sunlight. The second column gives you the number of observations per cell. The third column gives you the sample mean for that combination. In this case, the average height of the plants that received that watering frequency and that amount of sunlight. The final column then gives you the grouping information. Here's how you interpret the grouping information. If you have 2 groups that share a letter, then those means are not significantly different from one another because they're considered to be in the same group. On the other hand, if you have means or groups that do not share a letter, then those means are significantly different from one another. So here's what we can deduce from this output. First of all, plants that were watered daily and received a high amount of sunlight were significantly taller than all other plants. We can deduce this because these plants were in group A all on their own, and they didn't share a letter with any other group. The second thing we can say is that plants that received no sunlight were significantly shorter than all other plants, regardless of watering frequency. These 2 combinations shared group D, so there was no significant difference in their main heights. However, if they didn't receive any sunlight, it didn't appear to matter how frequently they were watered, because they didn't share a letter with any other combination. Finally, high sunlight appeared to counter being watered daily, in a similar way that being watered daily countered low sunlight. These plants were significantly shorter than those that were watered daily and received high sunlight, but they still grew better than those with no sunlight at all, or a low amount of sunlight combined with infrequent watering.